This is going to be a three-part question. But for the first part, we're just going to figure out the molar solubility of lead bromide in pure water. This is basically like asking what concentration of lead bromide is there in a saturated solution. I guess the first thing to understand is that when this stuff dissolves, there will be both lead and bromide ions in solution. Now, that stoichiometric coefficient of 2 in front of the bromide is important. That 2 means that we have to square the concentration of bromide in the solubility product constant expression. From the low value of the solubility product constant, we can see that not a lot of this stuff is going to dissolve. But if we want to figure out how much, we might want to do an ice table. Or not. It's not that complicated. The key thing here is there's twice as much bromide as lead. And we can use these equilibrium values in our equation here, putting in our value for KSP, and solving for x now. And this is the cubed root, and we've got ourselves an answer for x, which is not always the molar solubility. In this case it is. We said that x is the concentration of lead, and in this case there's a 1-to-1 ratio between the concentration of lead and the concentration of the whole compound. So because of this 1-to-1 ratio, because if 1 mole of the compound is dissolving, and also 1 mole of lead is therefore in the solution, therefore the molar solubility of this stuff is the same as the concentration of lead in the solution. So this value that we found is our answer, but just be careful for situations where x might not be the molar solubility, like this. For Mg3PO42, if you do an ice table, you'll get 3x for magnesium and 2x for phosphate, but the molar solubility would be x. But, alright, moving on. Part 2 of this question is, what would the concentration of lead be in a solution of KBr? So, specifically, what's the molar solubility in 0.5 molar potassium bromide? So now we're trying to dissolve PbBr2 in KBr. You might recognize that we have a common ion effect going on here. These compounds both have a common anion of bromide. So we're going to expect our solubility to decrease because this solution is already packed with bromide ion. And we have to shove more in there when we dissolve PbBr2. So the big difference here is that we start initially with 0.5 for bromide, and the rest of the ice table looks pretty similar. And I'm thinking ahead here. The solubility is going to be even less now, and it was already small before. So 2x is probably going to be very small compared to 0.5. So when we use our solubility product constant expression to solve for x, we might be able to drop out that 2x under the assumption that this term that's squared is going to be very, very close to 0.5. And that makes our equation a lot more simple to solve. And as you can see, indeed, the solubility is a lot lower than in pure water. Okay, so this problem has a third part, and the third part is starting in a different solution, dissolving PbBr2 into a solution where the common ion is lead. So dissolving it into lead nitrate, and the nitrate here doesn't really matter, it doesn't really affect the solubility. So here's what our ice table might look like. The big thing is that we're initially starting with 0.5 molar lead. And when it fills out, we get this. And we plug the equilibrium values into our KSP expression. And again, we assume x is small compared to 0.5. Oh, and we're not going to forget to square 2x. And I've worked out the algebra to solve for x here. And let's think about what we'd expect for our answer for this one. Now, because we do have the common ion, we'd expect it to be less soluble than in pure water. But we might expect more solubility with lead as the common ion compared to bromide, because this lead bromide, when it dissolves, it has to cram 2 Br minuses in solution for every 1 lead. So starting with some lead probably isn't going to be as impactful as starting with bromine. So when we actually run our numbers, we get this much, which is indeed between the solubility in pure water and potassium bromide.